So thank you very much. It's a pleasure to be here to talk about communication avoiding algorithms for linear algebra and beyond. I understand that you've seen these slides at least 30 times because there have been 30 speakers. So I'll go over them very quickly just to establish my notation, which is why we want to avoid communication in the first place. So my model is of a cost of an algorithm. I'm going to count the flops, and I'm also going to count how much data I'm moving around. And by data movement, I mean both kinds, either between a processor and DRAM, or between multiple levels of a memory hierarchy, or between processors over a network. So there's my communication model. My cost model is going to be very simple. I'll count the flops, I'll count the number of words moved, and I'll count the number of messages. What's a message? It's a bunch of contiguous words packed together. And each one of those has a cost associated with it, time per flop, bandwidth, and latency, the last two terms being the communication. And as we all know, the time per flop is really tiny, and it's much, much less than the time to move one word, which is reciprocal bandwidth, and that's in turn much, much less than the latency. And so not only are those terms very far apart today, but they're growing apart exponentially for all those technological trends which you've heard about 30 times already. And so these numbers are taken from an old NRC report, but they've been revalidated many times. And so avoid communication to save time. But that's not the only reason. The other reason is energy. And so here is a plot where the vertical axis is the energy on a log scale in picojoules it takes to do a particular operation, a double precision floating point operation, moving data on chip between registers, 1 millimeter, 5 millimeters, and moving data off chip. Blue is today's technology, red is 5 years from now technology. And so you can see that the difference is 1.5 orders of magnitude in energy between a flop and moving data off chip. And there's the on chip and the off chip. And if we go in 5 years, it's 2.5 orders of magnitude. So again, whether it's the battery in your cell phone that you don't want to die, or the $1 million per megawatt per year it takes to run a supercomputer center, you want to minimize communication to save energy. Okay, so now what are the goals then? I want to redesign algorithms to avoid communication. And that means between all levels of the memory hierarchy, L1 cache, L2 cache, DRAM, and so forth, the network. And if possible, prove lower bounds, that no matter how you implement an algorithm, there's a certain lower bound that says you have to communicate that much. And we have done that systematically, and I'll give you a bunch of examples. And it turns out that current algorithms, even ones that we thought were well understood, like matrix multiply, do not attain those lower bounds. You can communicate asymptotically less than current algorithms do, and so very large speedups and energy savings are possible. Now, you don't have to take my word for it that this is a good idea. You can take the word of someone at a higher pay scale, say President Obama. So here's a quote from the Department of Energy research request from a couple of years ago. And it says somewhere in the middle of page 65 that on modern computer architectures, communication is more expensive than floating point. And so to minimize communication, you need to reformulate the patterns specified by the algorithm. So when we first saw this, we were saying, what are they talking about? And so we went and talked to Mike Carew, who may have spoken here already, who's the architect of Trilinos, and he said what they were referring to are two algorithms I'm going to talk about today that we developed at Berkeley and now have been incorporated into Trilinos. One is communication avoiding GMRes, and the other one is a tall, skinny QR. Those are two of the algorithms I'll be telling you about. So here's the outline for the rest of the talk. I'm going to survey the state of the art of communication avoiding algorithms, and being from California, I'll use that particular abbreviation. And so I'll review the previous matrix multiply algorithms, which may again be a bit of a review from other lectures so that you know what the Naïve algorithm does and what it takes to minimize communication, what people thought they were doing to minimize communication. Then I'll tell you about 4 new algorithms in a bit more detail. Our new, I'll call it 2.5 dimensional matrix multiply. I'll explain why it is called that. Then tall, skinny QR. Another version of Gaussian elimination, which is asymptotically faster than the existing ones. As long as you abandon partial pivoting, we have to do something different. And then it all works for even more general linear algebra like Strassen's algorithm, and I'll tell you about the fastest matrix multiply in the world doing it that way. Now, when we first did all this, this was mostly, as you can see, for algorithms that sort of smelled like three-nested loops. Linear algebra smells like three-nested loops. And I will have a very careful mathematical definition of smells like in a few slides, but your intuition is perfectly good for now. And then we realized that could be generalized to any program that smelled like loops and that was accessing arrays. And so what we've done is that we've extended these lower bounds and some of the matching algorithms to any algorithm that basically accesses arrays. And so I will give you some summary of that theory. It uses some recent results in pure mathematics from functional analysis and group theory to actually do it, so it'll just be kind of a survey. And then I'll talk about communication avoiding Krylov subspace methods, which is an entirely kind of different approach. Okay, so here we go. And so let me tell you what the summary is. So for direct linear algebra, I'm going to tell you about lower bounds of communication for any problem that includes solving linear systems, least squares, eigenvalue problems, the SVD. They're mostly not attained by algorithms in the standard libraries, so the ScaLAPACK and LAPACK and so forth. So we are in the process of putting these new algorithms in these libraries. We've gotten a bunch of grants recently to work on this, and so large speedups are possible. Now, I'm going to give you a high-level kind of theory about how these algorithms work. There's a lot of tuning parameters, and so as usual, there's a lot of detail work to do, and we're trying to use auto-tuning and machine learning to choose some of these parameters to actually get the last few % out. But what the theory tells you is what's the right design space? What does the algorithm have to look like as a whole in order to get close? And then ditto for iterative linear algebra. Okay, so what are these lower bounds? So let me state them all for anything that smells like three-nested loops, so I'll call it n-cubed-like. The communication lower bound is going to depend on the amount of fast memory you have. So if it's a single processor, think of that as your cache. The slow memory is the DRAM. If you're on a parallel processor, think of M as your local memory. The rest of the slow memory is the memory owned by all the other processors. So here's what the lower bound says. If you have one processor and you assign it a certain number of flops to do, the question is how much data does it have to move in and out to do that? And the answer is the number of words that processor has to move is lower bounded by some constant multiple of the number of flops it does, divided by the square root of its local memory size. So it scales by the square root of its local memory size. More memory, the lower bound goes down. So in the case of, let's say, a single processor, this is all the flops. That one processor does all the flops. That's the cache size, and this is how much moves between cache and DRAM. If you're on a parallel machine, then imagine I've spread out everything equally among all the processors, and the number of flops is like the total flops divided by p. That's the easiest way to think of it, load balanced. And m is the memory that you're using on that processor. You may not use all the memory on that processor. It's not the cache size. It's whatever subset of the memory you actually use to solve your problem. So if you have n by n matrices spread out over p processors, m may be n squared divided by p. Each processor gets 1/p of all the data. So this has been known actually for quite a while for matrix multiply. It was first proved for the sequential matrix multiply algorithm back in '81 by Hong and Kung. It was extended to the parallel case in 2004. But it turns out it basically holds for everything that smells like three-nested loops. It works for the BLAS, LU, QR, eigenvalue problems, SVD, tensor contractions. Tensors are matrix enough like, three-nested loop enough like, they work. It works for some whole programs where you can have sequences of these problems. You know, you call a BLAS and you call LU, then you do something else. And so what the lower bound says is no matter how you take your sequence of subroutine calls and interleave them arbitrarily, right, some amazingly complicated optimization, this lower bound still applies. It works for dense and sparse matrices. I didn't say this number of flops had to be n cubed. It just has to smell like three-nested loops. So it applies to sparse LU perfectly well. And the number of flops as well, you may not know until you're done how many flops your sparse LU did, but that's what goes in the numerator, and that's the lower bound. It works for sequential and parallel algorithms, as I said, and there's no reason you have to do multiplies and adds in the inner loop. You could do graph theory stuff. So all pairs shortest path, Floyd-Warshall, that smells like three-nested loops, and it applies just as well. So that's the lower bound on bandwidth. How about the lower bound on latency, the number of messages? This is really simple. So if I have to move this many words, and I can pack them into messages of a certain size, I'll say that, think of it, it could be a cache block or whatever you want, the number of messages is clearly lower bounded by this quantity. And so what's the largest possible message size? It's clearly your whole memory. So this is maybe an unattainable, but sometimes attainable lower bound on the number of messages sent. It's just a factor of m times smaller than this one, because the biggest message is obviously limited by your memory size. And so I'm pleased to say this won a Best Paper Prize for the SIAM Linear Algebra Prize. So these are our goals. This is what we're going to try to attain. And as I said, all the algorithms in dense linear, and for LAPACK and ScaLAPACK in the dense case, often do not attain them. So our goal is to reinvent new ones. And for pretty much all of dense linear algebra, we've systematically reinvented all the algorithms and found algorithms that attain these lower bounds. And these algorithms are not just loop transformations. I mean, we need those too. For matrix multiply, you can think of it as just a loop transformation. But we have new numerical properties, new ways to encode the answers, new data structures. And so there's quite a bit of innovation required. The sparse case, there are a couple of examples. Sparse-Koleski On problems which are, have nice graphs, we understand how to do those and attain the lower bounds. But for arbitrary sparse matrices, we don't know. There's still lots of work in progress. OK, so that's a summary. And so what I'm going to do now is do a review of previous matrix multiply algorithms, start with a naive, work my way up through how people optimize it in the sequential case, and then get to the new stuff. So let me start with the most naive three-nested loop sequential matrix multiply you could imagine. Here it is. I loop over I, j, and k, and I update c sub I, j. And here's the picture. That particular entry is obviously the dot product of the ith row of A and the jth column of B. So let me just annotate this very naive algorithm with how much communication it does to see how bad it is. So let me just add some comments that say when the data moves in between the DRAM and the cache, because I can only do the arithmetic on the cache. So for each value of I will read in the ith row of A. Let me assume I can fit the ith row of A into cache. So I'll bring that into memory once and leave it there. And then I'll bring in Cij once. And then I have to bring in every column of B. So I'm going to read column J of B into fast memory. And at that point, my inner loop, my dot product, everything's in cache. And I can do the dot product and write C back to memory. So that's the naive algorithm. And so how many reads and writes do I do altogether? Well, I've read each row of A exactly once, and I reuse it. So that's n squared reads altogether. I read and write each entry of C exactly once. So that's n squared reads and n squared writes altogether. The bad guy is B, because every column of J has to be read in n times, because I'm doing it once for each vector. So I'm basically doing a vector times a matrix multiply in the inner loop. And so there's n cubed reads there. So I'm doing n cubed reads and a little bit more, and that totally dominates the cost of the 2n cubed arithmetic, right? Because these reads, that's the bandwidth cost, and it's asymptotically the same, n cubed and n cubed. I don't want to do that. So here is the very well-known way to avoid that problem. It's called tiled or blocked matrix multiply. I'm going to think of my matrices now not as collections of scalars, but as collections of blocks, and I have to pick a block size B. So every one of these little guys here is now a B by B block. Each of these guys is now a B by B block. I still have three nested loops over I, j, and k, but now I'm looping over blocks. So I'm looping from the first block to the n over bth block. And the inner loop still looks like the same inner loop as before, but now that's a B by B matrix, that's a B by B matrix, and that is a B by B matrix multiply, all of which fits in cache. So I'm assuming that I can fit all three of these blocks into fast memory at the same time. So 3b squared has to fit into M in order for this little trick to work. So now the question is, how much memory am I moving? And so here I'm going to read this block into fast memory, and I'm going to do it n over b squared times how much does it cost to move one block b squared. So there's n squared reads. Now here's the big win. Each block of A and B is of size b by b. Each one costs b squared to read it. But and how often do I read it in? I have three nested loops. Each loop goes from 1 to n over b, so it's n over b cubed times. Multiply that together, and I get n cubed divided by b. So now my cost is no longer n cubed reads, it's n cubed divided by b. And so I can go asymptotically faster if I keep making b and b bigger and bigger and bigger, right? I can make this term very small compared to that term. So the question is, how big can I make b? The answer is, I'd like to make it as big as possible. So, but I had an assumption for this algorithm to work. My assumption was that all three of those b by b blocks had to fit in fast memory at the same time. So that means that 3b squared has to be fit in fast memory. And so if I make b as big as possible, about the square root of m, then how much data have I moved? N cubed over b, that's n cubed over the square root of m. So that's where that square root of m comes from in this particular simple example. This doesn't say why this is true for anything that smells like three nested loops, but it tells you what, something that's been well known for a long time. How do you attain that lower bound for matrix multiply? So all of this assumed, to write the code, that I knew M, that I knew enough about the hardware in my machine that I could design the algorithm, pick the block size, depending on the hardware, and to write the code. But what if I don't know that, right? What if I'm trying to write portable code? Or what if there are multiple levels of fast memory? Here I was assuming there was one. What if I have L1 and L2 and I want to minimize across all of those? How do we write the algorithm? So obviously if you're at a company like Intel or IBM or any other company, you have a team of very clever programmers who spend their full-time day optimizing this by hand. And that's what they do. They have teams that do it. But that's not necessarily what we want to do. We want to use their work and take advantage of it. But there are a lot of algorithms that they don't do. In fact, we beat them quite frequently because we deal with cases that they're hand-tuned teams don't do. So how do we do that? So here's another way to go about the same code that deals with arbitrary numbers of levels of memory hierarchy, and it's called recursive matrix multiply. And so let me just remind you how to multiply 2 by 2 matrices. Write down the formula. It's very simple. There it is, all 8 multiplies and 4 adds. And this obvious little formula works whether this is really a 2 by 2 matrix and these are just numbers, scalars, or whether this is actually an n by n matrix and all of these submatrices are n over 2 by n over 2. This formula is still true, but now this multiplication there is not multiplying 2 scalars, it's multiplying an n over 2 matrix by an n over 2 matrix. So this tells me how to take an n by n matrix multiply and break it down into problems of half the size. And that naturally turns into code, a recursive subroutine. So this is recursive matrix multiply. I pass in 2 n by n matrices. If they're actually 1 by 1, I just do the right thing. Otherwise, I call this subroutine recursively to do that matrix multiply. See, there, this one multiplies A11 times B11, and it tells me that it's of half the size. So I have 8 of those calls, and then I add them. So each of these is a matrix multiply, and then I have 4 adds. So let me just repeat. So now let me ask, how well does this code do? So there's the code again, just repeating it. I need to write down some recurrences to say how much work does it do, how many arithmetic operations does it do, that's A of n, and how many words does it move, that's W of n. Since it's recursive, it's really easy to write down a little formula to figure it out. So the number of arithmetic operations this guy does, well, he calls himself 8 times on half the size, so there's 8 calls of problems of half the size. And then there's 4 adds, so that's 4 n squared over 2 adds. That's a nice simple recurrence. You can solve it, and it's exactly 2n cubed, because I'm doing the same floating point operations as the standard algorithm, maybe in a little different order. So that should be the same. What about the number of words moved? So again, it's going to be the same idea. How many words does this guy move? Well, I call him 8 times on problems of half the size. And then how much, and so there's that cost. And then I have all of these adds, so I have to bring in the inputs, write out the output, that gives me that. But that's only true if the problems don't fit in cache. Once n gets small enough so that everything fits in cache, this recurrence stops, and otherwise it just hits 3n squared. So it's almost the same recurrence, it just has a different base case. And when you solve it, you get what we expected, n cubed over the square root of the cache size. And so this is an example of a well-known algorithm called cache oblivious. It's oblivious to the size of the cache. M never showed up, it's still optimal. If I had multiple levels of cache, it still would have worked. And so people have been working on these algorithms for a long time. It's not a panacea. What if I ran this all the way down to n equals 1, right? I'd have so much subroutine call overhead, it would be ridiculous, right? At some point, you have to break off when n is small enough and call the hand-tuned blahs from MKL or wherever it happens to come. But still, this often gets large speedups. OK, so now, just to give you, let's see, make sure I'm. So I want to show you an experiment now to just emphasize to you, especially as students, how hard it is to write this kind of hand-tuned code. So what I did was, and I do this human experiment every spring semester when I teach parallel computing, I take a room full of students and I make them tune matrix multiply. I tell them all of the tricks. I give them all sorts of lectures on loop unrolling and cache blocking and all of this, and they have 1 week to hand-tune matrix multiply and race the hand-tune code from the vendor. So here are the results from when I taught this course and used this homework assignment back in 2009. I gave them, and so the horizontal axis is which team of students. Each of these little dots is a numbered, anonymized team of students, 2 or 3 students. The vertical axis is what fraction of peak they attained after a week of sweating over this homework. I gave them a code that ran at a whopping 14% of peak, and there is the hand-tuned code from the vendor, the ACML, and there's the incredibly clever graduate student instructor, the teaching assistant, Vasily Volkov, who you may know. He won a Best Paper Prize at Supercomputing for doing this work. So that's how fast he could go. And so you can see that even with all of this knowledge, then, and depending on whether you use which compiler you use, which intrinsic you use, which unrolling you use, the students still only got a tiny fraction of peak. But some of them managed to get reasonably close. So these guys were undergraduates that got that fast. And of course, we hired them in our lab, right? They're great. So that's the code we gave them. So the naive code, I should say, runs at 2% of peak. So if you do the blocking I just showed you about, no other tricks, you get a 7-fold speed up. You get a 14% of peak. That's the code we gave the students. And then the rest of this was doing all the other optimizations that you need to do to get the hand-tuned code and get the highest fraction. And so that, and when you do all that, you can get up to another factor of 6 up there. I mean, both factors are important, right? So what I'm telling you is that all the theory I'm telling you about, it doesn't give you all the answers. There's still a bit of work to do. So the next metric is how hard did these students work, right? Were some of them lazy? They didn't write very much code? So here's another plot. Each dot is a team of students. The vertical axis is the fraction of peak, and the horizontal axis is how much code they wrote on a log scale, right? How many hundreds of lines of code? We gave them 32 lines of code. The GSI had to write a couple hundred lines of code to actually get to 70% of peak. There are a few students who wrote 64,000 lines of code. Now, how did they do that in a week? Well, we told them about auto-tuning, so they had a week, they built an auto-tuner. They built something that tried all different variations and generated it, and we gave them credit for that. And so that's how many lines of code they generated. It was still, they still didn't beat the GSI. So anyway, this is just to give you a sense of what it takes to actually engineer some of these things. So that's the sequential case. Now let me tell you, any questions? Yes?
How many lines of code is the library?
So how many lines of code is in the hand-tuned code from ACML? You only can get object code from them. You don't ever see the source code from the vendor. So.
But I mean, how far away is x86 object code from a matrix kernel anyway?
How far away is which code? Intel assembly language from the hand-tuned MKL?
Yeah.
So we work closely with that organization. And some of our and they have, we don't beat them for the standard sizes that come up for square matrices where people benchmark and the sizes that come up in the panel factorizations in LU. But it turns out that for certain rectangular sizes, we beat them by 2 digits, large factors. They don't cover every case.
Let me rephrase the question. At that level, C and x86 look pretty close. I mean, the same number of lines of x86 are almost represented in C.
Right.
If they have a 60,000 line object code library, that's...
So I should say that this 60,000 lines were the number of ones that they tried, and not all of them were actually delivered as the final result. So this is perhaps not the best way to do the accounting of how much work they. This was sort of a measure of how hard they worked in a meta sense. Yes, John.
So Jim, I think what he's saying is you could compare the object code size of
Yes.
Right.
So we did not do that experiment. That could be certainly an interesting thing to do. So, but again, to follow up, which cases do they handle well? And because there's all these different dimensions. You have M and N and P, 3 different dimensions when you multiply matrices. And our experiments have shown they do unbeatably well for certain sizes and not so well for other sizes. So how do you do that comparison? Anyway, that's a good software engineering question. So now let me go on to the parallel case and tell you what's been known up until now for the best parallel matrix multiply. And this algorithm is called SUMMA, for Scalable Universal Matrix Multiply Algorithm. And so it's also called 2D matrix multiply because it's naturally described by taking your P processors and laying them out as a 2-dimensional grid, a P to the 1/2, a 4x4 grid in this case. So this picture not only represents the 16 processors, it represents the submatrices. So this processor owns that submatrix of A, that processor owns that submatrix of A, and so forth. So what's the algorithm do? So in general, I have to take the outer product of every column of A with every row of B and then add that to C, right? That's what the algorithm is going to do. So here's the idea. Let me take this column of A, or actually it could be a block of columns, so that could be not just one, but B columns. And what I need to do is broadcast it sideways. So this particular submatrix will be broadcast so that every processor owns a copy of it. That one will be broadcast sideways, and that one sideways. That all happens in parallel. Then I'll take that block row and broadcast it down. I'll take that sub row or submatrix and broadcast it down, that one and broadcast it down. So at this point, every processor has a copy of A, a little piece of A. It has a copy of a little piece of B, and now it just does a local outer product. It multiplies A call, it multiplies the red times the blue, and adds it to the green. And it's going to do that for every red block column and every blue block row. And so there's the code that does it, but that is the simple way the algorithm works. And it turns out that if you choose the number of columns in this red block correctly, then this actually hits the lower bound reasonably close, within a log P factor. And this uses the minimal memory. So my lower bound was number of flops divided by the square root of the memory size. So the number of flops is n cubed over P. It's load balanced. Every processor does an equal amount of work. And every processor just basically has one copy of the data. So that means that what the local memory it's using is n squared over p, well, maybe 3n squared over p. So that's what goes in the denominator. So let me just sort of summarize that algebra. So here is the summary of all the parallel algorithms that attain the communication lower bounds. So I'm going to assume I have n by n matrices on p processors. I just showed you matrix multiply. I'm going to assume I use as little memory as possible, a reasonable assumption for a slide or two. So that means every processor is going to own 1/5 of all the data, n squared over p. And so what are my lower bounds? It's the number of flops in the numerator, n cubed over p, divided by the memory size to some power. Number of words, it's m to the 1/2. Number of messages, it's m to the 3/2. So plug that in, and you get n squared over root p words moved, and the square root of p messages. So that's what SUMMA attains. And so let me ask what other algorithms attain those lower bounds. So let's look at ScaLAPACK. For the number of words moved, ScaLAPACK actually does attain this lower bound, except for the non-symmetric eigenvalue problem. It is asymptotically worse. But for the number of messages, it's almost always asymptotically worse. It usually sends vastly more messages than the square root of p, except for Cholesky. Cholesky is simple enough that people understand that well, just like matrix multiply. And so what we've had to do is systematically invent new algorithms that attain all these bounds up here, up to polylog p factors, so log p or log squared p, for everything else, okay? And so we've done that. And so that was, so we thought we were done for a little while, but then we asked, can we do better, okay? There's an assumption here that I made, and so why can we do better? Aren't we already optimal? Well, the assumption was that I was only using as little memory as possible. Now, if you've bought a supercomputer, you've spent all this money on the memory, you might as well use it, right? It's a hardware resource lying there. And so how, and the lower bound is still true if the amount of if I make m in the denominator bigger than the least amount I can get away with. And so the question is, can I attain it? So there was a special case in the literature that people had known for a while, and it's called three-dimensional matrix multiply. Remember, 2D matrix multiply was I took my p processors, laid them out in a two-dimensional grid. Well, I can lay them out in a three-dimensional grid. And it uses more memory. In fact, it uses a factor of p to the 1/6 more memory. So there's the local memory size. It's not n squared over p, it's n squared over p to the 2/3. And this algorithm has been rediscovered a few times, you can see. The processors are arranged in a grid that looks like this. And what each process, and so I can number the processors ijk, each index going from 1 to the cube root of p. And what does the ijkth processor do? It takes this subblock of A, multiplies it by that subblock of B, and adds it to C. And so we're each submatrix of that size. So this had been known for a while, but it wasn't very practical because it assumed you had this large amount of memory. And you don't always have that much memory available. So the question is, no matter what hardware you have to your disposal, M is given to you by whatever, by the operating system or by the hardware. I want to use all of it and go as fast as possible, whatever is available to me. It has to be at least minimal, but whatever is available, I want to use it. So let me tell you about the first new algorithm, which is communication avoiding 2.5-dimensional matrix multiply. So what I'm going to do, I'm going to introduce a parameter c, and I'm going to assume I have enough memory to fit c copies of the data spread out over the machine. So instead of n squared over p per processor, I'll have c times n squared over p. So c equals 1 is one copy, but it can be anything you like up to the 6th root of p. So what I'm going to do is I'm going to take my processors and arrange them not in a 3-dimensional grid or a 2-dimensional grid, by this 2.5-dimensional grid. So it's going to be p over c to the 1/2 by p over c to the 1/2 by c. And here's a little picture for 32 processors, 2 copies. So each layer here, each of the 2 layers is going to have a copy of the data. And so let me introduce those indices again so I can access all of the processors. And so initially, I'm only going to have data stored on the top layer. I'm going to start with 1 copy of the data. And so each of these processors will own a little subblock of A and B, the same as the picture as I had before. So what is the algorithm? It's pretty simple. So this processor is going to broadcast its copies of A and B down. So every layer is going to have a redundant copy of the data. So now, then, at each layer, k going from 0 to 1 up to c, each layer is going to perform 1/6 of the SUMMA algorithm. So the algorithm I showed you before, it's going to do 1/6 of the work. So it's going to compute 1/6 of all those outer products. Each layer will have a different 1/6 of the work. And then what I do is I do a reduction along each column to take all those partial sums, and the true sum appears on the top. Okay? And that actually attains the lower bound no matter how many copies of the data that I use. So the question is, what kind of speed up do you think we can get from doing this? Well, we got up to a factor of 12 speed up by doing this over regular matrix multiply. So here's an experiment on 16,000 nodes of an IBM BGP, which I think was at Argonne at the time, so 64,000 cores. And we did both an 8K by 8K matrix multiply and a 130K by 130K. And the vertical axis is percentage of machine peak. And no surprise, if I do the 2D matrix multiply, you get 5% of machine peak. It's ridiculous to use this many cores to try to multiply tiny matrices like this. But if I'm willing to use 16 copies, I can go 12 times faster. And if I'm, for this larger matrix, which is more compute bound, it's 2.7 times faster. So where's the actual time going? Let me sort of break down the timing here. And so this is the same data where I've broken down the time into communication, idle, and compute. And so here's the 8K problem, and here's the 131K problem. And it's normalized so that the 2D algorithm takes time 1, so that's 12 times faster, and that's 2.7 times faster. Now we can see that the communication reduced 95% on both cases. Here, the idle time went away. There was just a lot of idle time waiting for messages to go around. But even the compute time went faster, so that was a little bit surprising. And the reason is that this new algorithm is multiplying larger submatrices in each processor. So it's calling the local BLAs on larger submatrices, and it goes faster. And so that means the green bar also went down. So the whole thing was 12x faster. For this larger problem, you can see it was about a third compute, a third communicate, and a third idle. So even if we made all the idle and compute go away, we only went a factor of 3. But what the heck? If this is where all your energy went, maybe we saved you 95% of the energy. But still, this is worth doing. So, and I'm pleased to say this won a Distinguished Paper Award. So, so now let me tell you some sort of theoretical properties of not of this algorithm, but a lot of other algorithms. And they have a property I'm going to call perfect strong scaling. And so the idea is that every time you add a processor, every time you request a new processor, you get a new hardware resource, but you also get all its memory. You should use all that memory because you're paying for it. And so let me ask, how do I do this strong scaling? So every time I add another processor, I'm going to use all the memory on it that's available. So let me start with the smallest number of processors I can use to actually fit my problem in the machine. So for matrix multiply, I have p processors, each has m memory. That product better be 3n squared. And so I'm going to start with that, and I'm going to increase p by a factor of c. So c times as many processors, so that increases the total memory. And let me ask how this algorithm scales. So let me just do the algebra. So here's the model. I'm going to have a gamma sub t is going to be the seconds per flop, so multiplied by the number of flops. I'll count the number of words moved and multiply that by the seconds per word moved, so that's a reciprocal bandwidth. And I'll count the number of messages, and I'll multiply that by alpha. That's the time per message. And I'll assume my message size isn't the whole memory necessarily. It's whatever's convenient to the message passing system, so that'll be little m is the maximum message size. So there's the formula. And so this is the time to run on c times p processors. And there's sort of the whole messy thing. The only thing I want you to notice is how it scales. It scales perfectly. If I increase the number of processors by a factor of c, the flop time goes down by a factor of c, the bandwidth time goes down by a factor of c, and the latency time. Everything scales perfectly, so it runs exactly c times faster. That's perfect strong scaling in time. Now let me do it in energy. So I need some more notation to write down an energy model. And this is going to be a simple linear model. So I'm going to count the number of joules per flop, whatever that happens to be, the number of joules per word moved along the network, the number of joules per message. But that's not the only place that you spend energy in a machine. I also have the memory. So I'm going to have delta is going to be the joules per word per second to store something in memory, right, because I'm burning stuff there. And then there are all those other leakage terms that I haven't modeled. So I'm just going to say joules per second for everything else, right, the network cards and all of that. So I can write down a formula for this, and it gets longer and messier. But the point is, how it scales perfectly. It takes the same amount of energy to solve the problem c times faster on c times as many processors. You don't use any more energy. How could this be? I'm using c times as many processors. They're all using the same amount of energy, but they all run 1/7 as long, so the energy is constant. And so you can't do better than that. So let me go on with this story. So there are the formulas again, just so that you can admire them. I'm not going to go into the algebra anymore. The same perfect scaling extends to the n-body algorithm, same kind of ideas, extends to Strassen's algorithm. And so with all of these formulas, you can use these models to answer all sorts of interesting questions about how you either build algorithms or architectures. So you could say, what's the minimum energy required for a computation? How many processors, how much memory do I use to multiply matrices if my goal is to minimize the energy? You know, what subset of the machine should I use? If I have a time limit on how long I have, you know, I have to solve my problem within a certain amount of time, what's the minimum energy I need to achieve it? Right, so this is going to be, you know, minimize this subject to that is less than or equal to some upper limit. I can also ask if I have a maximum energy budget, what's the fastest I can run it? That's sort of a similar optimization problem. You can just write these things down. And you can also ask what is the minimum power, because that might be a separate kind of limit. In that case, you take, you know, the ratio of energy divided by time, that's the power, and say, how do I choose all the parameters? And finally, if you're a computer architect, and we have a grant from DARPA to work on this, you can ask if your funding agency has given you a target of gigaflops per watt. It happens to be 75 gigaflops per watt is what DARPA wants. Is it possible to build a machine that would actually attain it? What architecture, what values of these parameters, gamma t, gamma e, alpha, would get me anywhere close to 75 gigaflops per watt? So these kind of architectural models tell you, you know, give the architects a target. So they can say, well, I don't have any hope of making that number smaller, but I can make that number smaller, and they can go ahead and design their architectures. Okay, so that's what I wanted to say about 2.5D matrix multiply and some of the lessons. Are there any questions before I go on to the next algorithm? Okay, so now I'm going to go on to something that tastes quite different, tall, skinny QR. So the QR decomposition I hope people are aware of. I'm going to factor a matrix into an orthogonal matrix times an upper triangular matrix. And so here's the picture. So suppose I have 4 processors, and I decide to lay out my matrix so that each processor gets 1/4 of the rows. So processor 0 owns W0 and so forth. So here's the idea. Without doing any communication at all, each processor is going to do a local QR decomposition. So processor 0 will factor W0 into Q times R and so forth. Haven't done any communication yet. Now, that is not the QR decomposition, but I've made some progress. Let me just rewrite that as this is equal to the product of this block diagonal orthogonal matrix times this stack of 4 triangles. Right? So I want 1 triangle over here, 1 R factor, but I've gotten 4. So what do I do now? I take that stack of 4 and I pair them up. And I take these 2 triangles and I do its QR decomposition. So this processor takes this, you know, matrix and factors it into Q times R, and that one into Q times R. And again, it's not the QR decomposition, but I've made more progress. This is the product of this block diagonal orthogonal matrix in this stack of half as many triangles as I had before. And the last step is I take the last 2 triangles, pack them together, and do its QR decomposition. So what have I done implicitly? I have factored the original matrix into the product of that orthogonal matrix times that orthogonal matrix times that orthogonal matrix times R. That's the QR decomposition. It's not your, you know, QR decomposition in anybody's textbook yet, but it has all the mathematical properties that you need. It has, you know, you can do anything you want with it that you normally would do. But we have a different mathematical representation. The output is a list of all of these orthogonal matrices, but represented by householder transformations, the usual kind of trickery. But it's the same. Excuse me, the same R as you had before, and it's numerically stable in all the usual ways. Okay, so that's a parallel algorithm. So let me now abbreviate it by this picture, and you can see that all I've done is basically I've called MPI reduce, where the reduction operation is take 2 matrices, stack them on top of one another, and do a QR decomposition and pass the R up the tree. So this is all I'm doing is a reduction, where it's QR, and that's the parallel algorithm. So, but what about all the other, you know, architectures I'm interested in? What about the sequential algorithm? It's exactly the same. All I'm going to use is a different reduction tree, but it's exactly the same reduction. So suppose I can only fit 1/4 of my matrix into cache at a time. So I can fit W0 into cache or W1 into cache. So what do? I bring W0 into cache, do its QR decomposition. Then I bring W1 into cache, stack R00 on top of W1, do that QR decomposition, get R01. Bring W2 into cache, stack R02 on top of it, and so forth, and I read this from memory exactly once. 1 is the lower bound on how many times you have to read it from memory. So that's what so it's the same algorithm, just a different reduction tree. If I had a dual-core processor, it might look something like this. But what if I have a real computer? You know, it's multi-core and multi-socket and multi-rack and multi-site and out-of-core. You know, a little more complicated. I'm just going to choose my reduction tree dynamically. Whatever hardware I have available, I will choose the tree, you know, at runtime to do the right thing. And so what kind of speedups can we get from doing this? And so here are just some summaries of some old speedups in a whole bunch of different architectures. On Intel Cloverton, there was an 8x speedup on 8 cores. This is an old Pentium 3 cluster, a 6.7x speedup. Blue Gene 4x. This was an old Fermi Tesla GPU, 13x speedups. This was a grid. This was four different computers over 4 French cities. You can imagine how long it takes to move data between different French cities, or any cities over the internet. And so the most speed up you could possibly get is a factor of 4 because you have 4 computers, and it actually worked that way. It was all latency bound. And for the cloud, we have this running in the cloud. You can write it in a MapReduce framework in a perfectly natural way. The question is, how do you measure performance in a cloud environment? That's something that we're still kind of struggling with. But here's one metric, which is, suppose I just stream through the data once, right? That's sort of the fastest thing you can do in a cloud environment. We can do the QR decomposition and stream through it 1.6 times. So, we stream through the data twice, because we have to do it twice, and we're 1.6 times slower than that. That's sort of like how close we are to going as fast as we can. So those are all parallel speedups. Now what about the sequential case? The best case we had once was an infinite speedup. Now what do I mean by infinite speedup? So we compared the LAPACK implementation of QR to this one, and this was running on my student's laptop, Mark Homan's laptop, and if you ran LAPACK, it never finished, right? It was thrashing the disk. It took forever. We just sort of quit. But if you did it with a new algorithm, it was only 2 times slower than as though we had infinite DRAM, as though it all fit in fast memory, because we only had to bring it through memory once. So this is the tall, skinny QR. If you want to do the SVD of a tall, skinny matrix, it's the same cost, basically, because all the work is compressing it to this one smaller matrix. And so this is another good algorithm. So let me now take that idea that I just showed you about this sort of reduction tree, doing QR, and use it to do LU faster. Okay, so I'm going to use the same idea to replace partial pivoting. So the bottleneck in doing Gaussian elimination, it turns out, is how long does it take to choose your pivot? So imagine you did partial pivoting the classical way, right? Each time I get to a column in the matrix, I have to look for the biggest guy and permute him to be on the diagonal, right? That's how Gaussian elimination works. So that means for every column, I have to do a reduction. I have to do a max. That's going to be n log p messages, right? Or the number of messages is certainly going to grow proportional to n. I don't want to grow proportional to n. I only want to do root p. So how do I do that? I need to take a panel, and only do log p messages and still somehow find the pivots that go up there. It's going to be the same reduction, except now at every level in the reduction, what I'm going to do is I'm going to take a submatrix and choose its and let's assume I have B columns. I'm going to choose the B most linearly independent columns of rows and pass them up the tree. I'm going to choose P. So here's how it works. Every processor owns a quarter of the rows. Locally, they do Gaussian elimination with partial pivoting. They choose their B most linearly independent rows of their submatrix. And we're going to pass those up the tree. At the next level, I get B rows from one child, B rows from the other child. I put them together, do Gaussian elimination again, and get the B best rows from these pairs. And I'll get the B best rows from those pairs. And then I'll pass those up the tree, the B best from that half of the machine, the B best from that half of the machine, do Gaussian elimination. This is on a tiny matrix, one more time. And out at the top pops the B best pivot rows. Then what I do is I go back to the original data and use those B pivot rows as the original pivots. I put them up on the diagonal, and I do Gaussian elimination without pivoting. This is extra work to do this, but it's a lower order term, and I'll show you get good speedups. And there's a theorem that says even though it's not partial pivoting, that it's choosing a different set of rows than the normal algorithm would, it is numerically as stable as partial pivoting in a certain mathematical sense that I won't go into detail. So let me tell you how much faster this goes. And so I'll give you a model for an exascale machine that doesn't exist yet, and then I'll give you some performance data. So this is some performance modeling we did just for fun on an exascale machine. All these parameters like 1 million nodes, 1,000 cores per node, so that's 1 billion cores, 100 gigabit per second interconnect bandwidth. These were taken from some DOE exascale workshop from a few years ago. And we just plug those into the performance model, right? I've shown you the performance model for LU, for matrix multiply. LU is similar. And we asked, how much faster do we go? So here is a speed up plot where the horizontal axis is log of the number of processors. The vertical axis is the problem size, n squared over p. And it's color-coded by how much faster we predict the new algorithm goes than the old algorithm. And this is a little hard to read here. So it gets up to a factor of 29 faster because all of your time is spent in doing messaging it's the latency latency that the new algorithm is avoiding, and that gives you up to a factor of 29 in this particular architecture. So that's for a relatively small matrix on a lot of processors, right, where the message costs are dominating all the flops. Up here, there's no speed up at all. This is the land of the LinPack benchmark. You're spending all your time doing the flops, and the communication is not so relevant. It only helps when you're trying to use all the processors on a relatively smaller problem. So perhaps on future architectures where the memory per processor is smaller, then you can't even get up into this range. Okay, now let me show you some real speedups. And again, this is measured on a BGP. And so I'm showing it to you for without pivoting, and then I'm showing it to you with pivoting. And so here is the, so actually this is the, let me get this, tell you this straight. This is the so I have two innovations here. I have better pivoting. This is the communication avoiding pivoting. And I also have the 2.5D version of it, right, where I do replication of the data. So I have two innovations here to show you what the speedups are. So let me do no pivoting first. So certainly that's got to be faster. And here you can see the speed up from just doing the replication trick is a factor of 2x. Again, all the communication pretty much goes away and the idle time goes away. Pivoting costs more. So here is the communication avoiding pivoting, and you can see that the cost for pivoting is about a factor of 2. So to go from that level to that level. But it's certainly much better to do it in 2.5D than not. And again, the communication time has gone away significantly. So the two innovations are you have to do tournament pivoting, you have to do this tree reduction, and you have to do replication in order to get all these improvements. Okay, so that is a summary then of all the ongoing work, of all the work that I want to go into detail. Let me just summarize all the other things because linear algebra is pretty big. We have work on the rest of the BLAs, on symmetric and definite factorizations, on QR with pivoting. In that case, what's QR with pivoting means you want to put the most independent columns at the beginning, your pivoting columns. There are lots of other pivoting schemes like complete pivoting. There's eigenvalue problems. All pairs shortest path. We have world's fastest algorithm for that. We have both 2D versions of it where we're minimizing communication where you have one copy of the data, C equals one copy, and we have C greater than 1 copies. It turns out that the benefit of replication, of having C copies, is greatest for matrix multiply. It's not necessarily always the best thing for these other algorithms because it turns out that even though the bandwidth cost goes down when you replicate, the latency cost does not. And we have a new theorem which is almost ready to publish, which says that if you want to minimize latency, C equals 1, 1 copy is the best. If you want to minimize bandwidth, then C greater than 1 copies is best. And so there's a trade-off between the two. Depending on your architecture, on the relative cost of latency and bandwidth, it's not clear what C is a tuning parameter. It's not clear what the right value is. We're doing this on multiple platforms, so multi-core, cluster, GPU, all these different platforms, and we're trying to integrate it into all these different software packages. We just got a grant from NSF to redo LAPACK and ScaLAPACK to put these algorithms in there. And we're also putting it into various individual applications. So CTF stands for the Cyclops Tensor Framework. That's joint work with folks at Argonne. And that's an algorithm that does tensor contractions, which show up in quantum chemistry a lot, and that's being integrated into a package for use there. So let's see, I have until 10 o'clock, is that right? Okay, fine, I'm on schedule. So let me just do one more dense linear algebra thing because it's not an n-cubed algorithm, it's Strassen's algorithm, okay? And then I'll go on to beyond linear algebra. So let me just remind you of what the lower bound was that I told you about for classical n-cubed matrix multiply. This is the same formula I did before. I just wrote it a little bit differently. It's still n cubed over p, number of flops, divided by the square root of the memory size. I've just written it slightly differently. And the reason is to simplify the typesetting. What is the lower bound for Strassen? All I have to do is change 3 to log base 2 of 7, 3 to 2.81. And this is the lower bound for Strassen. No matter how you reorganize Strassen's algorithm, which does asymptotically fewer floating point operations, this is how many words of memory it has to use. It has to move. In fact, this is not just true for Strassen, it's true for any Strassen-like divide and conquer matrix multiply, and people have discovered others. Strassen's really the only practical one. And all I have to do is change log base 2 of 7 to whatever the magical exponent is, omega, right? And people keep inventing new omegas every year. I think the current record is 2.3 something, so, but anyway, this is the practical one in the middle. And it uses a completely different proof technique, which I'm not going to worry about right now. And to be Strassen-like, it has to be regular enough for the proof to work. And it extends up to, so it turns out this lower bound says it's always better to use more memory. There's a limit. There's a limit for the classical algorithm and for Strassen. So you can't use more memory than this particular magic formula. So you can, it gives you a limit in the number of copies of the data. So for example, for classical matrix multiply, the limit is this 3D matrix multiply. There's a similar limit for Strassen. And so change omega to 3 for classical. And I'm pleased to say this won another best paper prize. So the natural question is this lower bound attainable? So here's what the algorithm looks like, and it's sort of a general technique that works for other algorithms too. We call it communication avoiding parallel Strassen. And so we have a tree in Strassen, right? At every submatrix, we're going to break it into 7 subproblems, right? That's how Strassen works. And so here I have 2 pictures of that tree. So each of these is a matrix multiply of problems of half the size. And of course, this repeats recursively. So the question is, how do I traverse this tree? I have 2 choices, breadth first search, BFS, and depth first search, or DFS. So in breadth first search, which is the most parallel thing, I will take my P processors that I have available here. I'll break them up into 7 groups, and I'll assign P over 7 processors to each of these, and I'll run them all in parallel. That's breadth first search. The alternative is to take all P processors and do each subtree one at a time. And so each one is going to run faster, but I'm going to do them one at a time. So the question is, how do I choose between breadth and depth? Well, they use different amounts of memory. This one is going to use more memory because each one is there's some replication involved. This one, these problems are both half the size, so it's only a quarter of as much memory, n over 2 the quantity squared. So the question is, how do I choose? Here is the algorithm. I want to use as much memory as possible. That's how I'm going to hit the lower bound. So at each level in the tree, I'm going to say, if there's enough memory, and if I have at least 7 processors, I'm going to do it this way, because this will fit. I'll use all the memory that's available. Otherwise, I'll take a depth first search step and assign all my resources just to one node at a time. And this, in theory, hits the lower bound that I had in the previous slide. And it's sort of a tuning parameter. So this sort of tunes at runtime as to how fast you do it. So let me give you some performance numbers. And so the horizontal axis is the number of processors. This is strong scaling on a Cray XT4, an old machine, Franklin at NERSC. It's a 94,000 by 94,000 matrix multiply. The vertical axis is flops per node. So the way we do this is we say, let's assume each processor does 2n cubed over p flops, divide that by the time. So this really is proportional to inverse time. So up is good, right? That lets me compare Strassen, which is the red line at the top, the fastest, to, for example, ScaLAPACK, which is down here. So this says it's 3 times faster or something like that. So the thing to notice is that this red line is almost horizontal. That means I'm getting perfect scaling. I go from 49 processors up to 1,000 processors, and the speed up is proportional to the number of processors because it has that perfect strong scaling property. So I have a whole bunch of other algorithms here just for fun. So this green line here is ScaLAPACK, so the 2-dimensional algorithm. This green line is the 2.5D algorithm, the new one I told you about, and it's certainly faster. It's not as horizontal as we would have hoped, because on this machine, even though it's a 3D torus, it maps perfect. The algorithm gives you perfect speed up in a 3D torus, which is what you get when you ask for an allocation on a blue gene. The Cray XT4 is a 3D torus, but you get a random subset of the processors. So you get contention and stuff in the network, so you don't get quite perfect speed up. And these blue lines are previous attempts in the literature to parallelize Strassen, and they don't work so well. Okay, so, and this was invited to appear as a research highlight in the CACM. Okay, so that is the end of sort of the direct linear algebra. And so now I want to switch topics and go on to beyond linear algebra. How does all this generalize to arbitrary programs to any algorithm that accesses arrays? Okay, and for one particular example, I'll tell you about a new communication optimal direct n-body algorithm. So what I'm going to do is I have to sort of say, how do you generalize all the notation? So let me go back to sequential matrix multiply. So there's a naive code, 3 nested loops. Here is the block code where I iterate over blocks of size b, and the inner loop is a b by b matrix multiply. Okay, we've seen that before. And the theorem says that if I pick the block size to be m to the 1/2 by m to the 1/2, then I attain the lower bound, which is n cubed over m to the 1/2. So the question is, where do all these 1/2s come from? If I wrote down a different code that wasn't matrix multiply, how would I figure out where all these 1/2s come from? What would they change to become? So let me tell you what the new theorem says applied to this very simple example. So here's my code. all I need to know about this code to optimize it is which arrays have which subscripts. And so I don't care what it's doing. I just care about which arrays have which subscripts. I'm going to record all that information in this little 3x3 matrix, delta. There's one column for every subscript. There's one row for every array. And there's a 1 that says A has I as a subscript and K as a subscript and doesn't have J. So everything is in there. Okay? So then what I'm going to do is I'm going to solve a little linear program, a little 3x3 linear program for three scalars, xi, xj, xk. What am I going to do? I'm going to maximize the sum of these x's subject to the constraint that this matrix times the x's is less than or equal to 1. And the answer is a bunch of 1/2s and 3/2 is the sum. Okay, so this all seems magic. So what does our theorem say? Our theorem that applies to any code. For this code, it says the number of words moved is n cubed divided by m to the power, the solution to the linear program minus 1. So that's where that 1/2 comes from. And the optimal block sizes are m to the answers to the linear program, m to the 1/2, m to the 1/2, m to the 1/2. Okay? So now let me just do another example, which is n body, and say what the theory says here. So here I have 2 nested loops. I have a bunch of particle positions at I and j, and I compute some force, don't care what, and I update a force array. And so everything I need to know I'm going to record in this matrix. So I have 2 subscripts, I and j, and I have 3 arrays, right? I have f, pi, and pj, and this records who is a subscript of whom. I'm going to solve a linear program. This is an even simpler little linear program. Maximize the sum of the x's subject to delta times x is less than or equal to 1, and the solution is 1, 1, and the sum is 2. So the theorem says the number of words moved, the lower bound, is n squared, the total amount of work, divided by m to the magic exponent, m to the 1, and it's attained by block sizes m1, m1. I mean, this has been known for a long time. But what hasn't been known is that this also gives you a 1.5 dimensional n-body code, right? There's 1-dimensional n-body, there's 2-dimensional n-body. People have known that before. But now we have everything in between. We have the 0.5D n-body. We can use as much memory as possible. So here's some speedups. And so this is for 32,000 particles on 8,000 cores. This is ridiculous. 4 particles per core, right? It seems like I'm going to be totally overwhelmed by communication cost. But no, we get perfect speedup. So here is 1 copy of the data. So the vertical axis is the execution time. So down is good. Horizontal axis is how many copies of the data I use. C equals 1 is 1 copy, out to 64 copies. Green is communication, red is computation. And by the time I have 64 copies, I'm getting perfect speedup, even though there's still only 4 particles per core. And so you can see this is a good idea there too. We got a like 11.8x speed up. Now I have 2 versions of C equals 1. That's because BGP has 2 networks. It has the reduction network and it has the regular torus network. The reduction network was better for this, but the reduction network is gone. They don't build them anymore. So I think it's gone on BGQ. So this is the only part of the network that's available. Okay. So now, let me do one more example just to give you a sense of how general this is. I just wrote down random code, okay? 6 nested loops. The loop indices are I1 through I6. I just made up a bunch of arrays. I put in a bunch of subscripts just to see what would happen. And all I need to know about this code, I record in this matrix where there's 1 row for every array and 1 column for every index, and I just put a bunch of 1s and 0s, so I know who's a subscript of whom. Again, the theorem says just solve a linear program, maximize the sum of the x's subject to delta times x is less than or equal to 1, and out pop these magic numbers, and their sum is 15/7. And so the theory says that no matter how you reorganize this algorithm, if you want to go as fast as possible and minimize communication, you can't do any better than n to the 6th divided by m to the power this number minus 1, so 8/7. And what is the optimal block size for it? Well, it's m to the 2/7, m to the 3/7, m to the 1/7. That just comes from solving this linear program. So this works quite generally. So let me try to tell you where this all comes from. Are there any questions though, about what the theory looks like? Yes?
The linear program can have an infeasible solution.
You say the linear program can have an infeasible solution. That means you have unbounded reusability. So if you were taking an array and writing it over and over again without having to have any memory accesses, then you would have an infeasible linear program. So the linear program would tell you that. Right. So all of that sort of will follow, yes. So at this point, I have to tell you a little bit about the theory. So let me tell you where the proof comes from for the lower bound and then how it generalizes to arbitrary code. And the original proof idea was in this paper which was just about matrix multiply and generalized it to the parallel case. So let's suppose that we can bound the number of useful operations that we can do, call it G, if I only have m data available. So I have m entries of my 3 matrices, they're sitting in cache. And is there some way I can bound the amount of useful work I can do, multiplies and adds? Let's suppose I can do that and call it G. So now, in order to solve my problem, I have to do a certain total number of operations, call it f, n cubed in the case of matrix multiply. So that means that if I can only do, that means I have to fill the fast memory f over g times, because every time I fill it up, I can do g pieces of work, so that means I have to do it f over g times. How much does it cost to fill up the memory? M times f over g. Okay? So that is my lower bound on how much work I can do, on how many words I have to do. And the hard part is upper bounding the amount of useful work I can do given a certain amount of available data. So the question is, how do I do that? And so to attain it, I also need to, that's another problem. But right now, let me just give you an idea of how do I get this upper bound and how much useful work I can do if I only have some arbitrary subset m of all the available data. And so here's the geometric picture of how the proof works for matrix multiply. It'll give you some intuition for the general case. I'm going to represent my 3 nested loops by a cube. So there's an I direction, a j direction, a k direction. Each of these cubes is going to represent one of the inner loop iterations. It's going to represent, for the example, this one is going to say, please multiply a, that entry of A, times that entry of B, and add it to that entry of C. So this face, each square in this face represents an entry of A, each square in that face represents an entry of B, and each square there represents an entry of C, and each cube says take that face, multiply it by that face, and add it to the top face. Okay? So that's going to be my geometric representation. And so the question is, if I can have at most m entries of A, so m of these squares, and at most m of those squares, and m of those squares, how many cubes does that cover? How many cubes can I sort of do? So let me just draw that picture again. And so here's my A, B, and C faces. And let's suppose that, just to make it really simple, that I have this many entries of A, that many entries of B, and that many entries of C. Then clearly they cover this kind of brick in the middle, right? I have all the data that I need to do all the multiply adds that are sitting inside this brick. So how big is the brick? Well, if this is x by y by z, if that's the size of the brick, how big are the faces? Well, this face is x by z, that face is y by z, and that face is x by y. So I want to bound the volume, x times y times z, in terms of the areas of the faces. They're the 3 areas. And it's pretty easy to see if I just multiply them all together, I get 2 copies of each factor, so I have to take the square root. And so the volume, the number of multiply adds, is equal to the product of the faces, areas, taking the square root. Okay, and that's m to the 3 halves. So each of these can be at most m. So that's the very simple case, but I want this to work no matter what subset of the data I pick. I mean, I picked a brick to make it easy to see, but for the theory to work, no matter what black blob I pick in the middle, I want to have an upper bound that looks like this. So here's the theorem from Pure Mathematics from 1949 that gives us the answer. Suppose I pick an arbitrary subset of multiply adds that I want to do. What data do I need to do it? Well, I have to take its shadow or its projection on the B face. That tells me what entries of B I need. I project it in that direction. I get its A shadow, and I project it up. I give it my C shadow. So what I need to do is say, how big can this black blob be if I know that the shadows, the size of the shadows is bounded by m? Okay, the theorem from Loomis and Whitney from 1949 says that the volume of this cube, the number of cubes in the 3-dimensional set, is bounded below by almost exactly the same formula. Take the product of the 3 areas, the area of the 3 shadows, and take their square root. So no matter what shape this is an upper bound. It's attained if it's a brick, but it's always true. Okay, so that's going to be my G. And so that's where it comes from. So now the question is, how do I generalize this to arbitrary code? So again, let me just do the notation step by step. There's matrix multiply. And so all I need to know about it is that I'm iterating over some subset of 3-dimensional space, some subset of triples of integers, and I'm accessing locations which are the subscripts of the 3 matrices, A, B, and C. These are my projections onto the shadows. Okay? So now, what's the general case? Suppose that I have some arbitrary set of nested loops or some recursive thing, but I'm iterating over some space. And now my inner loop can have arbitrary numbers of arrays and subscripts, and the subscripts can be whatever you want. I1 plus 2 times I3 minus I7, any linear functions of the subscripts that you want. I can have indirection, I can have pointers, that's okay. This is still, the point is that 3 times I4 is a linear function, and then that gives me a unique location in memory. That's all I need. So it can be, I can have sparse matrices and complicated data structures, and I can have as many lines of code as I want. It doesn't have to be one line of code. And all I need to do is recognize I'm iterating over some subset of k-dimensional space, because I have k indices, and all I have to do is capture these subscripts. And so here's some mathematics. These are called group homomorphisms. So all I have to do is capture these lists of linear functions into these linear transformations or group homomorphisms. That's all I need to know about the code. And so the question is, can I bound the number of loop iterations given bounds on the areas of these projections? So S is the brick in the middle of the blob. And so this is the cardinality of S, the number of points in S, so the size of the black blob. And these are the shadows. So this is the C shadow, the A shadow, and I'm counting cardinality. How many points are in each of those? So that's the bound I want to get. That'll give me the G to write down my theorem. OK, so notation again. I'm given a subset of k-dimensional integers, and I have all of these subscripts, group homomorphisms, and I want to bound the number of points in the black blob in terms of the sizes of the shadows. So it turns out there's a linear program that's going to do this. It's named after 3 famous mathematicians. If you took functional analysis, you may have remember Holder's inequality. Well, it goes back to him back in the 19th century. And it was updated by Braskamp and Leap in 1976. So here's the linear program. For all subgroups of k-dimensional integers, additive group, I want this linear inequality to hold. What does this say? Take the rank of that group. That's like the dimension of a vector space, same idea. The rank of that group has to be bounded by these unknown parameters, those can be solutions of my linear program, multiplied by these other integers, the ranks of these projections, dimensions of subspaces. So here's the theorem that was proved by a team of pure mathematicians back in 2010, including my colleague Michael Christ at Berkeley, Terry Tao at UCLA, who's like the smartest mathematician in the world, and some other guys too. So what they proved is that given any S that satisfies this linear program, then the number of points in that black blob is bounded by the product of the shadows to those powers. So this is half, half, half in the case of matrix multiply. So in our theorem, which builds on that, says that given a program with array references, which are given by those group homomorphisms, what you're going to do is take this linear program and solve it. Minimize the sum of the S's subject to this linear constraint. Then that gives you a lower bound of the number of words moved, no matter how you run the program. It's the number of iterations divided by m to the solution of the linear program, minus 1. OK, so that is going to be our goal for arbitrary code that accesses arrays. Can we do this? So the obvious question is it attainable? Are there any questions about that? Because there's a lot of notation here before I go on to talk about its attainability. OK, so let's ask if it's attainable. So the first question is, obviously, can we write it down, right? I mean, so if I look at this, I said this is a linear program. For all subgroups, I get a linear constraint. How many subgroups are there? There's an infinite number of subgroups, right? So this looks like an infinite number of constraints. But it actually isn't, because each of these ranks is an integer in a small range. It's an integer between 0 and the number of loop iterations. And the number of nested loops, right? So 3 in the case of matrix multiplies, right? So there are not very many possibilities here. It really is a finite set of constraints. It really is a linear program. But this is not a very concrete way to write it down, right? So the question is, can we write it down? So our first attempt to do that was bad news. It turns out that to write down every linear constraint is equivalent to a famous open problem in pure mathematics called Hilbert's 10th problem over the rationals. So if you remember Hilbert's 10th problem over the integers, that was proved undecidable by Maciejewicz and various other people in the mid-60s. So that's undecidable. So what is Hilbert's 10th problem is you got a bunch of polynomials. Is there a solution? So to the simultaneous system of polynomials. Over the integers, it's undecidable, been known since the 60s. Over the reals, it's called Tarski decidable. That was also proven back in 1949. But for the rationals, nobody knows. So we were kind of stuck here for a little while. Then it turns out there is another linear program that gives you the same solution. It is decidable. It has a crazy expense right now, but still, these are very small linear programs, so I don't care if it's exponential necessarily. So we're still working on that, but it is decidable to write down that lower bound. And even better news, that if for certain special cases of programs which come up very frequently, it's really easy to write it down, right? So I showed you a bunch of those delta matrices. They were full of zeros and ones. Just say who's the subscript to whom. In those cases, it's obvious. You just write it down. And in fact, even in the general case, it's easy to get approximations. You get upper lower bounds, even if you don't write down the exact linear program. So given all that, is it attainable? Of course, it depends on the loop dependencies, right? If your loops, I haven't even talked about loop dependencies yet, but if each loop if they have to be executed in one order because of the loop dependencies, then you have no optimizations whatsoever. You can't reorder it, and you can't do anything. But as long as you have some freedom, so the best case being no dependencies, or reductions are okay, that's matrix multiply, so that you can reorder them any way you like, then you can frequently attain these. We've never not been able to attain the lower bounds. So our open conjecture is you can always attain them. We've only proven that in a few cases. And so in the simplest case, which includes matrix multiply and n-body and database joins and things like that, if all of your subscripts are just subsets of the indices, i's or j's or k's, then the dual of that linear program, that the Holder-Braskamp loop linear program, tells you the magical tiling, the optimal tiling. So there was the linear program. In our theory, there's the dual linear program, and that's the one that I was showing you before that popped out the half, half, half for matrix multiply. And so it also extends to unimodular transforms of indices. So these don't actually just have to be I and j and k. They can be simple linear combinations. They have to be unimodular. So what is the ongoing work here? We are still working on accelerating this decision procedure. We think we can write it down very simply if you have at most 3 arrays or 4 loop nests. It's sort of an ongoing work. As I said, we're conjecturing that we can always attain it. We haven't found a counterexample yet. All of those perfect scaling results in time and energy extend. So you get these n.5D algorithms for all sorts of different codes. And this is something every compiler should be able to do, right? I mean, once we get it fully automated. And indeed, we have some DOE grants with folks in the audience, John Mellercummy, for example, back there. We're working on figuring out how this stuff should go into compilers. OK, so that's the end of direct algorithms. And in my final hour of my talk, I will talk about Krylov subspace methods. But are there any questions? Yeah, I think that's the next part of the talk. So the question is, how do you deal with stencils of repeated matrix vector multiplies? And I will talk about that right now. Okay. Right. And we can, if I actually don't answer your questions, that's what the question session is for. Okay. So let me go on to Krylov subspace methods. And so what I'm going to do is take a problem which consists of k steps of an iterative solver, which is useful in sparse matrix vector multiply for solving linear systems or solving eigenvalue problems. It also comes up in multiple applications of stencils, but let me concentrate on these two. And so in and there are a lot of algorithms like this, and I assume you've had a bunch of lectures. So conjugate gradients, GMRes, Lanczos, and Arnoldi. So what is the inner loop? I'm going to take a starting vector, a matrix, and I'm going to do k sparse matrix vector multiplies, SPMVs with that. That's where the communication is that I want to minimize. So what I'm going to do is try to minimize the time I spent communicating both with the matrix and the vector and for all the other things in the inner loop, dot products and so forth. So let me assume the matrix is going to be well partitioned. So if so 2D meshes, 3D meshes are the examples you should have in your mind. And so let me compare the serial implementation, conventional to new. So in the serial implementation, I have this loop. The inner loop does matrix vector multiply. The matrix is too big to fit in cache. So every time through the loop, I have to stream the matrix from slow memory to fast memory. And so my communication cost, the bandwidth, is going to grow proportional to the number of steps of the algorithm, right? So that's conventional. The new algorithm is going to move the data once from slow memory to fast memory and take k steps, right? One is a lower bound. And so I'm going to take k steps of the algorithm and move the data once. So what about the parallel case? So imagine now I've spread my matrix and all my vectors out over p processors. What's the conventional cost? I'm going to have k steps. Each step is going to have nearest neighbor communication, but it's also going to do a reduction. I'm going to have dot products. So the number of messages is going to grow something like k log p, because each reduction is going to cost log p. So the new algorithm is going to not depend on k. Again, I'm going to take k steps of the algorithm and do log p messages, right? So that's going to be the goal. And so there's lots of speed up possible here. I'll show you both modeled and measured values. The prices are going to be, one, there's going to be some redundant computation, but the whole goal here is to say that flops are cheap, so I don't mind doing a little redundant computation. And there are also a number of challenges, and we've made a lot of progress. So one is, what if your matrix is not well partitioned? You can't find good separators. Well, we can deal with that in some cases. How do you deal with preconditioning? Because people often run preconditioned methods. We have some preconditioners where this works well and some where it doesn't. It depends on your preconditioner. And I'll spend more time on numerical stability, because the obvious way to reorganize these algorithms are not numerically stable. You have to be clever to make them actually get the right answer. But let me tell you what the basic ideas are. And I'm going to illustrate it with the world's almost simplest sparse matrix. It's going to be a 32 by 32 tridiagonal matrix. So I can show you every last dependency and every last bit of communication. So I'm given a vector x of length 32. Each dot represents a vector entry. And I want to compute all the entries of ax, a squared x, and a cubed x. And so what I can do, since the matrix is tridiagonal, is draw every last dependency. So that entry of ax depends on 3 entries of x, and there they are. And to make the art a little bit better, I'll just draw that as a triangle. So the guy at the point at the tip of the triangle, that vector entry depends on the 3 entries at the base. And of course, this picture reappears everywhere. I'm not going to draw it everywhere. So that entry of a cubed x depends on those 3 entries of a squared. And if I just continue out the dependencies, eventually that depends on all those 7 entries of the original vector x. And so if I have one processor, for example, it wants to compute all those entries of a cubed, eventually it does really need all those entries of x at the base of that trapezoid. So now, let me tell you what the algorithms look like. So the sequential algorithm, let's suppose I can only fit a quarter of the matrix into cache at a time. Then I'll bring in those entries of x, all the corresponding rows of A, and then I have all the data that I need to compute everything in that blue trapezoid. That's step 1. Step 2, I bring in these additional rows of A and entries of x. I leave these 2 diagonal slices, ghost zones if you like, behind. And then I have all the data that I need to compute everything in the red parallelogram. Then I compute the green parallelogram and then finally the yellow trapezoid at the end. And I've read everything from memory exactly once, which is my goal, and I've computed all sort of 3 stages. So that's sort of the obvious sequential way to do it. On a tridiagonal, which is very simple, I have to generalize that. What about the parallel case? So now I'm going to try to assign, if I have 4 processors, each processor is going to have the job of computing 1/4 of all the entries of ax, a squared x, and a cubed x. So processor 2 will be responsible for that rectangle. And so what's it going to do? The classical algorithm would send a message to get that entry and send it to processor 2, that entry to send it to processor 2. Then I'd have another message for that entry and another message for that entry. So I'd need 3 messages with each of my neighbors in order to get all of the ghost zone data. I don't want to do it with 3 messages. I want to do it with 1 message. And so the obvious thing to do is to collect up all of those 3 pieces of data that I eventually need, and in 1 message, send those 3 words from processor 1 to processor 2, send those 3 words from processor 3 to processor 2. Now processor 2 has everything he needs to compute everything inside the red trapezoid, and so it can continue with the same volume of communication. I still need those 3 pieces of information, but with 1 message instead of 3. So that's where that factor of k goes away in the latency cost. And so every processor is going to do the same thing. And so here we see where the redundant work is going to be. Processor 2 is responsible for everything in there. Processor 3 is responsible for everything in that trapezoid. And where they overlap at the ends, those triangles are computed twice. But again, these are going to be small things on the boundaries. So this idea, I think the oldest reference for it was 63. And then I was talking to Belville Kahn, and he thought there was a reference from the 50s. So anyway, this idea of, this was, of course, drum memory they were trying to minimize access to. But this kind of idea for these simple patterns has been around for a while. But fortunately, it generalizes to arbitrary sparse matrices, as long as we can find good separators. So let me draw a picture of an arbitrary sparse matrix, a symmetric matrix here for simplicity. So each vertex represents a row or a column, and each edge represents a non-zero, the usual picture, the way we represent sparse matrices. And I partitioned it here, so these orange lines represent a good output of a graph partitioner. So I've chosen them so that it's load balanced, so that there's about an equal number of edges inside each partition, and so that there's a minimal number of edge crossings. And you can call your favorite graph partitioner Scotch or Metis for that. So the question is, how do I choose to do this, so as I said, use graph partitioning, and if it's a non-symmetric matrix, you have to use hypergraph partitioning in order to optimize this, because now the communication is going to be these guys. And so how is the algorithm going to work? So I want to do the sparse matrix vector multiply for everybody inside this partition. So to do A times X, I need all the dependencies that follow out one edge, so I need all the red guys. To do A squared times X, I need to follow two edges out, and so I need to get all the green colored ones as well and communicate them in. And to do A cubed times X, I need to follow three edges out and get all the blue ones as well. So in order to send all the information to the guy in the middle, the processor, to do A squared and A cubed, I need to collect the red, the green, and the blue into one message and send them so there's one communication with each neighbor. And so the number of communication steps has gone down by a factor of k, the number of inner loop iterations. And so as I said, this is a graph partitioning problem. So that's the parallel case. What about the sequential case? I need to choose some order in which to execute these. In the tridiagonal case, I went from left to right, and it was perfectly natural. Here, it turns into the traveling salesman problem. That will give me the optimal order in which to execute these different partitions and to minimize communication. So that's going to be our basic building block. So what this is going to do is in one communication step, I'm going to take a vector x, a matrix A, and it's going to give me all of these vectors, right? But that's not what I need to run conjugate gradient or GMRes. They use different vectors, but this is still my building block. This is what I know how to do. So now let me go on to the next step and say, how do I use this to make GMRes, for example, run faster? So what does the GMRes algorithm? I want to find the x in this space, in this Krylov subspace, that minimizes the residual. That's the mathematical definition of GMRes. And here's the classical implementation. I'm going to take k steps. I do a sparse matrix vector multiply. I get my next vector in my Krylov subspace. Then I run modified Gram-Schmidt. I do a bunch of dot products and Saxbys to make W orthogonal to all the previous vectors. And then I update a little tiny k by k matrix H. And at the end of this problem, I solve a least squares problem, little k by k least squares problem. So what I need to do is convert this into communication avoiding. So I'm going to have a different basis for the Krylov subspace. It's going to be this basis, not that basis. These vectors are not the same. But it turns out I still want to make them all orthogonal. I still need an orthogonal basis. How do I get an orthogonal basis? I run the TSQR algorithm that I told you about before. That's the tall, skinny QR. That gives me the same Q. These Q vectors are then the same, essentially, as these V vectors I got out of there. And I can rebuild my little H matrix from my R matrix, and then I solve my least squares problem with H. So here, this is communication avoiding, that's communication avoiding. And this algebra changes, I won't show the details. And so in the sequential case, I've won. The number of words moved is decreased by a factor of k. And in the parallel case, the number of messages is decreased by a factor of k. But there's a terrible numerical bug in this program. Does anybody see it? Everything is correct in exact arithmetic, but there's a numerical error. Yes?
If your power k gets large enough, you will end up with the round off.
Right. So I'm running the power method, right? This is, if you like, what Google does to do PageRank, right? All of these vectors are becoming more and more nearly parallel to one another, parallel to the dominant eigenvector. So they form a terrible basis of this Krylov subspace. And so I'm going to lose precision. But let me do a numerical experiment just to see what happens if I do this anyway. So I'll run it. And so this is a rather ill-conditioned matrix. The horizontal axis is the number of inner loop iterations. The vertical axis is the log of the residual, which I want to go down. Red is non-restarted GMRes, sort of the classical algorithm. The black is classical restarted GMRes, where I restarted every 192 steps. That's the black line. The blue line is the algorithm I just showed you, where I take a power of 8. So I'm only, a power of 24. So I'm going to take the matrix to the 24th power to try to save communication. It doesn't converge at all, right? It's just sort of giving me random noise. But I have a lot of freedom. So this basis fails to converge. And I'm going to call that basis the monomial basis, because if I look at these as polynomials, a squared, a cubed, those are monomials in the matrix A. But the world is full of different polynomials. I don't have to pick monomials. And so if I pick a different polynomial basis, it converges perfectly well. So all I have to do is pick the right set of polynomials, and there's a lot of numerical analysis theory about how to choose those polynomials. So these vectors are as independent as possible, then I get a nice independent basis and life is good. So let me just show you some speed up numbers. So this is a bunch of along the horizontal axis are a bunch of different sparse matrices from different walks of life. The vertical axis is the time relative to the new algorithm. So down is good. So the new algorithm is always at time 1. And this is the new way of doing it, and this is the old way of doing it, which is 2.3 times slower, 2.1 times slower. And this is running on an 8-core Intel Cloverton. This used all the tricks I was telling you about in 2 different ways. It's minimizing communication both on-chip, off-chip. So it's doing the sequential optimizations. It's also minimizing communication between cores on the chip. So it's doing the parallel optimizations too. So you have to apply both sets. And it's color-coded by where the time is going, because there's both the sparse linear algebra and the dense linear algebra. And so the purple stuff is the modified Gram-Schmidt time, the dense linear algebra, and the classical algorithm. And the blue is the sparse matrix vector multiply in the classical algorithm. I should say, we optimize the heck out of the classical algorithms. This is as fast as you can make sparse matrix vector multiply go. And so here's the new algorithm. And so here is the new kernel, the matrix powers kernel, we call it. And so the sparse linear algebra shrank from blue to red, and from blue to red, and from blue to red. That made a big difference in sometimes. But the dense linear algebra shrank from the purple down to the orange and the yellow. So the purple shrinkage was at least as important depending on the problem you were working on. So I'm going to show you convergence plots in a moment. And that all comes out with no problem. That doesn't cost extra. But this is the speed for one iteration you can think of. So we can stop early, but the idea here is that typically you're going to be running these for hundreds of iterations. And so if I overshoot by 7 out of 100, and I'm going twice as fast all the time, it's probably worth it. That is the yeah. Okay. So the first time, actually, let me tell you one other story about how hard this is to implement. The first time we did this, we had one student optimizing the sparse matrix linear algebra and doing a very good job. Another student optimizing the dense linear algebra. We put it together, and it slowed down dramatically. It was terrible. That's because the sparse kernel and the dense kernel were fighting one another over the resources. Then we realized what we had to do was go back and co-tune the kernels so that they were sharing the resources appropriately, and only then did we get all these speedups. So that means that you can't have independent teams doing this kind of work anymore. It has to be tuned at the higher level algorithmic level. So here the change in the algebra was not so dramatic. Let me just show you what happened for BiCGStab, which we did more recently. So this is a widely used algorithm too. It's a short recurrence. It's much cheaper than GMRes. So here's the classical algorithm. It's not very long. I won't try to tell you what all it's doing in there. And here's what it looked like when it finally got rewritten. So it took quite a few algebraic transformations to actually get it to work. So here are so in this algorithm, you have to multiply both by the matrix and by its transpose in order to get this to work. And so we have multiple calls to the kernel, both for A and A transpose. But those can be merged, and the communication can be overlapped between those two. And all of these dot products, here we go, turned into a matrix multiply to compute the Gram matrix. Okay, I'm almost done here, so a few more slides. So you were asking about convergence. So let me just put up a convergence plot here for a particular matrix, which is, it's in the notes PD 900 from the University of Florida collection. It's not very ill-conditioned. It's a condition number of 120. And so the horizontal axis is iteration. The vertical axis is residual. Here's Naïve BiCGStab, and here are the other versions of it. Not even the Naïve algorithm manages to converge down to machine epsilon. That's because there are 2 different recurrences in BiCGStab. There's a recurrence for the residual, and there's an independent recurrence for the solution. They can become decoupled, and at some point, it forgets where it is, and it stops. And that is also true for our new algorithm using a Chebyshev polynomial basis. It's true whether we use a Newton basis. Those are the different choices of basis polynomials. And if we use a monomial basis, it doesn't work very well. So there's a well-known trick in the literature called residual replacement by van der Vorst and Yee that goes back a while. And every once in a while, what you have to do is reset the iteration to recalibrate so that the residual and the approximate solution correspond to one another again. And there's a very cheap recurrence that you can maintain that tells you when it's time to do that. And if we do that, then everybody converges just fine, and it goes all the way down to machine precision. And it may take they don't converge in exactly the same number of steps, but they do a pretty good job. And so the monomial bases had to do this residual replacement far too often at iteration 7, 15, 24, and the other guys had to do it just a couple of times, and that guaranteed that they got all the way. So these are some of the numerical analysis issues that you need to do. So I'm almost done here. So here's a summary of all this work. We have new lower bounds, optimal algorithms, big speed-ups in theory and practice. There's lots of open work going underway. I told you about GMRes, and by CGStab, there's a lot of other algorithms that we've done, and there's more underway. Recognizing which versions are stable and which ones are not stable is a bit of an art at this point, so hopefully we'll make more progress there, but we do have stable versions of everything so far. For preconditioning, I said some matrices worked and some didn't. If you have a diagonal or a block diagonal preconditioner, those are easy to incorporate. More general preconditioners are harder. The ones that seem to work best are hierarchically semi-separable, about which I think you may have heard some lectures. So that class of preconditioners seems to work here. And there's also lots of different kinds of sparse matrices that people come up with. You don't always represent a sparse matrix by a list of indices and a list of non-zeros. You can have stencils where you have repeated data. There's lots of variations on this where this works. So for more details, the website at the top, bebop.cs, has lots and lots of papers and code to do some of these things. You can take my whole semester course on parallel computing, and there's a few weeks in there which go into this material in a little bit more depth. And last semester it was broadcast by the National Science Foundation, so you can have their pre-recorded version too. And it's going to be run again in the spring semester, and there's going to be free supercomputer accounts for anybody who wants to do all the homework. But of course, you've been doing homework for 2 weeks, so maybe you're tired of it. That would be fine. This is a joint project with lots of people. I won't try to break them down. There's lots of people at Berkeley, Kathy Ellick and I, who spoke earlier. We're sort of the co-PIs on this activity. And there's lots of people at many other organizations who are doing it too. So let me conclude by saying it's time to redesign all linear algebra code, n-body algorithms and software and compilers, and the thing it all has in common is don't communicate.